So, in today's lecture we will continue with the discussion on maxima minima and we will formalize the statement we made last time. So, for a what we did last time, if you recall, for a possible maximum or minimum at x naught, where x naught is a stationary point, a critical point, we have decided to call it critical point, some call it stationary point, critical point, that is grad f at x naught is 0. We wanted to do the second derivative test, and what we did, we said something like sine of f of x naught plus h for h small minus f x naught h small norm of h small depends on sine of QH. That was informally what we did, and what was QH? QH we define half of the second term in the Taylor series, summation I equal to 1 to n, j equal to 1 to n, del square f, del xj, del xj, hj, hi, where h is this vector h1, h2, hn prime. Now, as far as the sign is concerned, this fellow is doing nothing, right. This is simply a constant. So, this is we have also written as h prime. So, everything evaluated at x naught, I keep on forgetting that. So, this is h prime, Hessian f at x naught h. This is Hessian, I mean one should not confuse with this h. H f at x is del f del square f del xi del xj at x naught 1 to n 1 to n. Okay. So, we will make two assumptions here, okay, and we will see. One assumption is necessary that in our, so we have actually discussed about it last time, we have also assumed it. Assume that second order partial derivatives are all continuous. Continuous at x naught, and also assume that determinant of the Hessian at f x naught is non-zero. I will come back to this assumption later, why we need that, maybe this lecture, end of lecture or next lecture. So, if determinant of h of f x naught is 0, we call x naught a degenerate critical point, and in this case this second derivative case test will fail. it will not give you anything, as the proof will suggest. You will see, if you see the proof, you will see that if this determinant is 0, the second derivative test does not work. It is simply like that if you do the function of one variable, if f double prime at that critical point, f from a function from interval to r, f prime at some x naught is 0 and if double prime x naught is also 0, then second derivative test for one variable also fails. Similar situations also occur here, and in this case, degenerate case, we have to do further test either by observation or by going to higher derivatives. Anyways, so since we are only concerned about sign, we forget about this half part and take our QH. Since we are half will not change any sign, so we will take QH to be this thing. If you want to keep half, no problem, but this time I have to write a half. So let us forget about the half part. Okay. The first observation you made here that if you have any lambda in real, then q of lambda h for any h, so this lambda will be multiplied with each of the component here. So lambda is each of the component where, and it occurs twice, so it will come out to be this. So if I multiply with any lambda, sign of QH does not change, it remains same. Sign of q lambda h is sign of QH for any lambda in R. This is needed for scaling, as you will see. So let us suppose that first case 1, q of h is greater than 0, suppose for all h in Rn. Okay. Then I write this way, f of x naught plus h minus f of x naught is equal to, okay, I have taken out half part, so maybe I write half QH. Why? I am writing Taylor series expansion. Remember that it will have grad f at x naught dot h, but grad f x naught, this is 0. So it will actually start at QH, correct, plus I will have error term. So I will do it only for second order term, second order Taylor series expansion. Okay. Now look at this fellow, infimum of QH, infimum of QH h in Rn and norm h equal to 1. Let us call it m. My claim is this m is bigger than 0. Why? Well, QH is always bigger than 0 for all h in Rn. Norm h equal to 1, this is a circle, right. Now in circle, in the very first second lecture or second lecture of this course, we have shown that if I have a continuous function, then it attains its maxima and minima over a compact set. This circle S1 is a closed and bounded circle. This is the set of all h such that norm h equal to 1. This is a compact set. So on that compact set, infimum will be attained, because Q is a continuous function of H from definition, and infimum is greater than 0 because QH is greater than 0 for all H, and on a complex, if certain continuous function is greater than 0 on a complex set, its infimum is also greater than 0. That is very easy to prove. Okay. So, what does it say? That if I take any H in Rn, then if I look at QH by norm H by norm H is on the circle, because H by norm H has norm 1. So, this will be greater than equal to M, because M is the infimum, which implies from this equality that for any H, Q of H is greater than equal to M into norm of H square for all H in Rn. Very good. So, what about Fx naught plus H minus of Fx naught? From there, this is greater than equal to M into norm of H square plus norm of H square EH. Now, EH is the error term. So, can choose a delta greater than 0 such that if norm of H is less than delta, then E of H, M is a fixed number which is the infimum, this is less than let us say, I should have put a half here, no? If I have a does not matter. So, so just say anything 1/4 by M. So, that should show that f of x naught plus h minus of f x naught is bigger than equal to, so there is a half here, 1/4 M H square, which is always bigger than 0 as long as H is non-zero, and H equal to 0, this is f x naught. That shows for norm of H less than delta, f of x naught plus H is always bigger than f of x naught, correct. So, that is for all y in a neighborhood of x naught, this sign is bigger than, so x naught is a local minimum. So, if QH is greater than 0 for all H in Rn, then x naught is a local minimum. Now, maximum part is easy. Next, if I have QH is less than 0 for all H in Rn, then apply 1 this part for minus s. Okay. How does it help? Because you will see that H minus f at x naught is equal to minus HF at x naught. So, and so a local minima for minus f is a local maxima for f. So, if this is so, I will get from the same consideration x naught is a local maximum. Apply everything this analysis for minus f. So, that solves the question for minus f as x naught is a local minima or maxima when QH is either greater than 0 or less than 0. So, third possibility, there exists H1 in Rn such that Q of H1 is positive and H2 in Rn such that Q of H2 is negative, that is H attains both positive and negative sign. In that case what happens? In that case my claim is that X naught will be a saddle. How? Well, so again the same situation, grad of X naught is 0. So for a fixed H and for any lambda in R, you look at this fellow, f of X naught plus lambda H minus f of X naught. So in R2 there is U, okay, here is my U, here is some X naught, H1 is somewhere here and H2 may be somewhere here, I do not care. Actually without loss of generality, by translating I can say that X naught is 0. So this is translation, so this is 0 without loss of generality. You just look at U minus X naught, it will have same kind of property. Okay, what is that? Follow the geometry. This is equal to Q half, okay, lambda H plus lambda square H square E lambda H, which is equal to half of lambda square QH plus lambda square. So let us take the lambda square part out. Now again the same idea, if I choose lambda, let us say mod lambda less than some delta, here is a lambda square there. So E lambda H is the error term, so I can have E lambda H, this is less than 1/4 of QH, right. So in particular if I apply to H1, so I will have H1 here, H1 here, everything H1 here. So sign of this fellow in this case f x naught plus lambda H1 minus f of x naught, Q of H1 is positive, so this will be positive. Similarly, choosing lambda some less than some delta prime, I can make E lambda H2 less than 1/4 of Q H2, and in that case I will have f of x naught plus lambda H2 minus f of x naught less than 0. So what is happening? Now lambda is any arbitrary number less than delta, H is somewhere, assume x naught is 0. Now multiplying by lambda I can always bring it to a neighborhood around 0. H1 whatever be the H1 multiply by suitable lambda, I can always bring E lambda H1, sorry lambda H1 near a neighborhood around 0. So that means I can make, so if I take delta naught to be minimum of delta and delta 1, I can bring x naught plus lambda Hi in B x naught delta naught. So I have a point x naught plus lambda H1 minus f x naught is greater than 0. So if this is greater than 0, f a lambda x naught plus lambda h 1 is greater than f x naught, and f x naught plus lambda h 2 is less than x naught, and that is precisely the definition for x naught is a saddle point. So, this is the so called second derivative test for function of n variable. Okay, so, go through the proof again. You have to at least go, you have to go through it at least twice, then you understand what is going on here, very easy, but still go through it once again, and I will do an example for you to end today's class. Let me write down the example, I have already written down for it. F from say R3 to R, f of x y z equal to x y z x plus y plus z minus 1. So, I have to look for critical point first. There may be many, and in this case there are uncountably many actually. As you see, this will be equal to 2 x y z minus 2 x y z minus y z, right here. Del f del y, this will be 2 x y z minus z x, and del f del z will be 2 x y z minus x y. Okay. So, if I put grad f at x equal to 0, then if I assume x not equal to 0, y not equal to 0, z not equal to 0, then the solution is, only solution is you can find x equal to half, y equal to half, z equal to half. X equal to 0, y not equal to 0, z not equal to 0, x equal to 0, y not equal to 0, z not equal to 0, but this is equal to 0. So, this is not possible. Similarly, x not equal to 0, y equal to 0, z not equal to 0, x not equal to 0, y not equal to 0, and z equal to 0, they are all not possible. Okay. So, one solution, but if you see any of 2 from x y z is 0 are 0, and other anything, other arbitrary, possible. That is are all critical points for any z, for all x, for all y, all z. If you calculate the Hessian f at x, that turns out to be 2yz, 2yz minus z, 2yz minus y, 2yz minus z, 2, just a minute, h f x, f x, x, del f del y, 2xz, sorry, 2xz, and 2yz minus y, 2xy minus x, 2xy minus x, 2xy. I think I made a mistake here, del fx del fx del x x2 yz minus z 2 yz del f del y del x minus z del f del z x 2 yz minus y, ठीक है, yeah. So, HF at half is equal to half 0 0 0 half 0 0 0 half. So, QH is always equal to how much? You can check QH is always QH half of H prime HF at half H, this is always greater than 0. Okay. So, this is local minimum, whereas HF at let us say x 0 0, if you check determinant of this is same as determinant of HF at 0 y 0, same as determinant of HF at 0 0 z equal to 0. So, these critical points are all degenerate, and we have not so far deduced any test for degenerate critical points. So, we will talk about this test in some other language. Something from linear algebra is happening in the next lecture.